So we've talked about discontinuities in rational functions. Discontinuities occur when there is an x value that makes the denominator of the function equal to 0. We have these things called vertical asymptotes. Vertical asymptotes, we said, are a vertical line that the graph gets closer and closer to, it never touches. But in a function, you can find the vertical asymptote algebraically. So in this function in problem 2, y equals x plus 1 over x minus 2, x minus 3. The first thing I want you to look for is if any of the discontinuities are removable. That means, can you do any canceling? There is not any common factors in the numerator and denominator to cancel. So that means that for the denominator there are two values of x that will make the denominator 0. And those two values are positive 2 and positive 3. And they are both vertical asymptotes. Remember that the other thing we need to do in order to find vertical asymptotes is we want to make sure that the numerator and denominator of the polynomial are factored. So you have to go back to your old factoring techniques in order to do this. Now we're going to talk about how you find horizontal asymptotes. Horizontal asymptotes don't exactly have a mathematical formula for doing it. There's no algebra really to do. However, this is a concept that leads us into a concept in calculus called the limit. So you can think about it like, hey, I'm learning some calculus today. There are three things that can happen, and I'm going to write this different from the way the book does, because the book does it in a very formal fashion, and I think that the way that I do it will be easier for you to understand. Okay, there are three things that can happen when you have a rational function. So here's the first one that can happen. Let's say that I have y equals 5x minus 3 over y equals 2x plus 1. I want you to notice that the degree of x is 1 in the numerator. That means the exponent of x is 1. And I want you to know that the biggest degree of x in the denominator is also 1. If the degree in the numerator and denominator are the same degree in the numerator and denominator, then the horizontal asymptote is the ratio of the coefficients of those x's. So there's a 5 in front of the x on top and a 2 in front of the x on the bottom. So the horizontal asymptote is y equals 5 halves, or 2.5. I'm going to take that same equation, but I'm going to alter it just a little. Instead, I'm going to do 5x minus 3 over 2x squared plus 1. And the reason I did that is because now the degree of x in the numerator is 1, but the degree of x in the denominator is 2. When the degree in the denominator is the bigger one, or you can say when the degree in the numerator is less than the degree in the denominator, then the horizontal asymptote is y equals 0. That means it's the x-axis. Okay, so the degrees in the numerator and denominator could be the same, or the degree in the denominator could be bigger, or the last thing that could happen is the degree in the numerator could be bigger. So, again, I altered this just a little. So now the degree in the numerator is 2, and the degree in the denominator is 1. When that happens, there is no horizontal asymptote. That means there is no horizontal line that the graph gets closer to but never touches or crosses. You don't have to actually do any algebra, and you don't have to do any factoring to determine this. Let's do an example. So here in problem 3, I want to find the horizontal asymptote of each rational function if it exists. Let's see if I have enough space to write my word. Find horizontal asymptote. All right. So in the first rational function, y equals 2x over x minus 3. The question is, Is the degree of x in the numerator and the denominator the same? Is the numerator bigger or is the denominator bigger? Well, the degree is the same. That means the horizontal asymptote must be y equals 2 over 1. Okay, let's try this again. Y is equal to x minus 2 over x squared minus 2x minus 3. So the degree of x in the numerator is 1, but the degree of x in the denominator is 2. When the denominator is bigger, the horizontal asymptote is y equals 0. Y equals x squared over 2x minus 5. So the degree of x in the numerator is 2, the degree of x in the denominator is 1. When the numerator is bigger, there is no horizontal asymptote. The reason we're finding horizontal asymptotes and vertical asymptotes is because we're going to use that to help us draw sketches of rational functions. Okay, the last thing that we'll do in this particular video is we'll talk about how to go through the process of graphing, or getting at least a partial graph, so that you can draw a decent sketch of the rational function. So on a graph, y equals x squared plus x minus 12 over x squared minus 4. You've got to factor the numerator and denominator. The numerator is going to factor into x plus 4, x minus 3, because those are the two numbers that multiply to give you negative 12, but when you add them, get you positive 1. And the denominator is a difference of two squares. It factors into x plus 2x minus 2. Notice that nothing is removable, which is good because a removable discontinuity is a special type of discontinuity unto itself. It's called a hole. Next, let's find the vertical asymptotes. The vertical asymptotes you're going to get by setting the denominator equal to 0. So the vertical asymptotes must be at negative 2 and positive 2. So I'm going to start drawing a general sketch of this. Here's my coordinate plane, and here's my vertical asymptote at 2 and my vertical asymptote at negative 2. Alright, next thing I'm going to do is I'm going to find the horizontal asymptote, and I'm going to look back at the original function. The biggest degree of x in the numerator is a 2. And the biggest degree of x in the denominator is also a 2. That means that the horizontal asymptote is going to be a ratio of the coefficients in front of those terms. The horizontal asymptote is going to be y equals 1 over 1. That means at 1 there is an asymptote here. Alright, what's going to happen is these rational functions, the vertical asymptotes, are going to tell me that the graph is in 3 different sections. And how I'm going to graph them kind of depends on some stuff like x-intercepts, y-intercepts. So now let's go and find the x-intercept. Remember, the x-intercept is where y equals 0. The x-intercept is where the numerator, x plus 4, x minus 3, equals 0. So it turns out that the graph is going to hit the x-axis at negative 4 and at positive 3. So it's going to hit here and it's going to hit here, however this curve works. The y-intercept is where x equals 0. So in the original function, if I just plug in 0 everywhere there's an x, 0, 0, 0, I get negative 12 over negative 4, which is positive 3. So 1, 2, 3. So there's a y-intercept here. So I know that part of the graph is going to be in here somewhere. The other two parts of the graph must be on the opposite side. This is kind of how it's going to work. So the graph is going to look like that. Let's practice that one more time. Here's an extra example. Y is equal to x plus 3 over x squared minus 6x plus 5. The first thing I'm going to do is I'm going to factor the denominator. The numerator can't be factored. The two numbers that multiply to give you 5, but add to give you negative 1, are x minus 1 and x minus 5. I have no removable discontinuities. The first thing I'm going to do is I'm going to find my vertical asymptotes. The values that make the denominator equal to 0 are 1 and 5. So I'm going to start drawing a little graph here. There's a vertical asymptote here at 1, 2, 3, 4, 5. And then there's one here at 5. The next thing I'm going to do is I'm going to determine what the horizontal asymptote is. Well, biggest degree of the exponent in the numerator is 1. But the biggest degree in the denominator is 2. If the bigger exponent of x is in the denominator, the horizontal asymptote is y equals 0. So that means here's my horizontal asymptote. All right, so this graph is going to be in 3 parts. The vertical asymptotes define the 3 parts. So the graph kind of normally alternates. Like one part will be above the horizontal asymptote, and then it'll be below, and then it'll be above, or vice versa. So the next thing that I need to do is I need to find the x-intercept. The x-intercept, where y equals 0, is what makes the numerator equal to 0. Well, the x-intercept is at -3. So 1, 2, 3. So that's not an x. Hold on. Yeah, okay, so that's an x-intercept. Now let's find a y-intercept. The y-intercept is where x equals 0. So if you plug x into the original function, if I look back at the original function, these all become zeros, and I find out that the y-intercept is 3/5. That just means it's a little bit less than 1. So if here's 1, 3/5 is maybe here. Okay, so now what I can see is at least over on the left-hand side, it's probably going to curve up like this. That means in the middle portion, the graph must look like this. Oops, let's make that look a little bit better. Ugh, like that. Which means that the third portion must look something like this. It's at least a general sketch of kind of what's going on. Another thing that you could do, if you're trying to figure out a sketch, but you don't have a graphing calculator to figure it out, you could figure out some ordered pairs that lie in this graph. So maybe check some ordered pairs at x equals 2, 3, and 4, and see if those ordered pairs are above or below the x-axis. Are your y values positive or negative? And you would get negative y values. And that's how you would know where your graph is. And then 5 is a discontinuity, so maybe try 6, 7, and 8, and see if you get positive or negative y values. That's going to help you out determining what the sketch is going to look like.